So here we've got two radio towers. They're both broadcasting the same signal, except that one of them has a phase shift. We're specifically told the phase shift is pi over 2 ahead of the other one. So when we say that one of the towers has, or one of the sources has a phase shift ahead of the other one, that means that's got a higher value for phi, little phi. And that basically just represents that they're out of sync with each other. One of them emits a crest while the other one emits the same crest a little bit later. Emit a crest and the other one emits a crest. They're out of sync with each other, as opposed to crests at the same time, troughs at the same time. And for electrical devices like radio antennas and speakers, that's usually just a matter of the way they're wired up in the first place. So if they're wired the same, that means they're in sync with each other and there's no difference in phase shift. If they're wired oppositely, they're exactly half a cycle apart. Here though, they're pi over 2 apart. That's what fraction of a full cycle?
Is that a quarter?
Yeah, that is exactly a quarter cycle, offset. So that means that that's going to cause some strange changes to the usual interference. So let's write out what we know. We know that, first of all, we're going to need to deal with the total phase difference. This formula here. And we know specifically that the phase values are going to be offset by this much. And we'll want to choose a direction for subtraction. Do you want to subtract A minus B or B minus A here? Okay, let's go with B minus A. Doesn't really matter which direction you subtract as long as you're consistent about it. So I would recommend choosing a direction, making a note to yourself and to anybody who might be reading your work, just as a reminder to make sure you keep the same order all the time. And then we know that the delta total phase, or sorry, delta phase shift, little phi, is going to be pi over 2 minus 0. So that's positive pi over 2. So we know delta little phi, and that should be the same all the time. If you walk around, you're changing the distances, but you're not changing these sources. And so the delta phi doesn't change. We assume that both of the radio waves arrive at your location at the same time. What do we know about the frequencies? They're the same. So that means delta phi is going to be delta frequency, this value minus itself is going to be 0. And also lambda is a constant. If the frequencies are the same, then the wavelengths are the same. So lambda is a constant and can be pulled out of the delta. So that means if we rewrite this equation a little bit, we know this entire time term is 0 because there's no difference in frequency and there's no difference in time. We know lambda is a constant and can be pulled out of the equation, or pulled out of the delta, I mean. We know delta phi is positive pi over 2. Also, we specifically want, no signal at all. How do we guarantee that there's no signal at all at the location where we stand? Yeah, we want destructive interference. And what does delta total phase have to be to guarantee destructive? Right, 2n plus 1 pi, some odd number times pi. And you could write that as odd times pi. And then just keep in mind, I would just treat odd as the word odd as a variable. And then at the end, you can plug in various odd numbers for odd. Or you can write it as 2n plus 1 pi, because 2n plus 1 is guaranteed to be an odd number. And then at the end, you can just fill in various whole numbers, odd and even, for n, and that'll get you an odd multiple of pi. So let's try working this out. We know frequency, so we can find lambda as needed. And let's try that. How would you use the frequency to find the wavelength? Yeah, we can use the idea of velocity. Velocity times frequency equals wavelength. So that means wavelength equals speed over frequency. We know the frequency is 3.75 times 10 to the 4th hertz. And what can we use as the speed here? What kind of wave is this? Yeah, an electromagnetic wave, also known as light. Radio waves are just a type of light. You've got visible light in a certain range of wavelengths. So light has a variety of different possible wavelengths, anything from, I think it's something like 300 nanometers to 800 nanometers, somewhere around there, is visible light. Anything with a longer wavelength than that or a shorter wavelength in that range is going to be light that you can't see. Your eyes are only adapted to see light in a certain range of wavelengths. So anything beyond that spectrum still counts as light, also known as electromagnetic waves or electromagnetic radiation. It's just different wavelengths of light. You could even say different colors of light. Radio waves are just a different color of light that you can't see. X-rays are a different color of light that you can't see. Microwaves, gamma rays, these are all just different wavelengths, different colors of light that are outside of the spectrum visible to humans. And since this is light, it's going to have a speed that is the speed of light, usually written as c. And that is pretty close to 300 million meters per second, 3 times 10 to the 8th meters per second. Tremendously fast. In fact, the fastest speed possible. It's not really something special about light and its speed. It's just that 300 million meters per second is the speed limit for the universe. You can't travel faster than that because that's how fast causality spreads out. It's basically the speed of speed itself, I guess you might say. So light is traveling that fast simply because it's going as fast as possible and it can't go faster than that. So we fill in that speed for speed of light. And we want to divide that by 3.75 times 10 to the 4th. And hertz is the same as 1 over second, so we may as well write it like that. So when we divide those, we can divide individually 3 over 3.75 and 10 to the 8th over 10 to the 4th. What is 10 to the 8th over 10 to the 4th? Yeah, we can just subtract the exponents, so we get 10 to the 4th. And then for units, the seconds cancel out, so we just get meters. And then 3 over 3.75, I think that works out to 0.8, 4/5. So we get 0.8 times 10 to the 4th meters, or alternatively, how else could we write that? What do you get if you multiply 0.8 times 10,000? Yeah, 8,000 meters. Also, since the other distances in the problem are given in kilometers, we may as well write this as 8 kilometers. So that's what we'll use as wavelength. Wavelength equals 8 kilometers. Alternatively, you could leave it as 8,000 meters and convert the other distances into meters as well. But I think we may as well use kilometers as is already given. So that's our wavelength. We can fill that in for lambda here. So negative 2 pi times delta x divided by 8 kilometers plus pi over 2. Any questions on that so far?
Yeah, once more. How did we get c over f, lambda equals c over f?
That's originally from the idea that speed is wavelength times frequency. The distance per cycle times cycles per second. So cycles cancel out, you get distance per second. Then you divide both sides by frequency. So wavelength is speed over frequency. But since we're specifically talking about radio waves, which are a form of light, the speed is going to be speed of light.
Oh, okay.
Any other questions on that? So it looks like the main thing we still need to deal with is the distance, the delta x, because the answer we're looking for isn't the delta x. The answer we're looking for is where do you stand? So we want to be able to translate between where you stand versus what the difference in path length is. So let's say you're standing at some location. Let's say you are standing here. not necessarily at 3.5 or whatever, but just some arbitrary location. And we want to know the difference between how far those waves travel. How far wave A travels to get to your location. So we'll call that XA. And how far wave B travels to get to your location. We'll call that XB. And we don't know what those values are, but we could start assigning some variables to them. For instance, A, if the wave is traveling from A, it looks like our coordinate system from 0 to 8 is already set up as distance from A. So we may as well just use XA as our variable. Let's say XA is just some distance, let's say some distance D. How would you write XB in terms of that? If this distance is D, how would you write this distance? Yeah, that's 8 minus the distance already covered. Because we've got these two distances, they have to add up to 8. XA plus XB has to add up to 8 total. And so if XA takes up D amount of distance, XB is whatever's left when you subtract D from 8. You could also write that algebraically. You could say XA plus XB has to add up to 8. And then just subtract XA from both sides. 8 minus XA. And we're calling that XAD. So those are our distances, the path lengths traveled by each of the waves. And then to find delta X, we can just subtract XB minus XA. So delta X, XB minus XA. Subtract those and what do you get? What's going to combine there? If we've got 8 minus D, yeah, 8 minus 2D, because you got 8 minus D minus another D. So that's 8 minus 2D, which means we can replace delta X completely with 8 minus 2D. So let's fill that in. Delta X is exactly the same as 8 minus 2D. And then we can start simplifying. First of all, what shows up in every single term here? Yeah, so we can just divide both sides by pi to cancel that out completely. Divide both sides by pi, and we're going to cancel out a pi from every term being added up. So we get 0 minus, that'll just be negative 2 times 8 minus 2d divided by 8 kilometers plus 1/2 equals 2n plus 1. And then what? How else could we proceed from here if we want to solve for d as the unknown distance, the unknown location? Is there anything we can reduce or simplify or get rid of? Yeah, we could subtract 1/2 from both sides. Actually, yeah, let's try multiplying by 8 first. If we multiply both sides by 8 kilometers, that would at least clear out all the fractions. So let's try multiplying by 8 kilometers on each side. This isn't strictly necessary, but I think it's going to make the numbers easier to work with. That way, in the first term, we multiply by 8 kilometers, and that cancels out the denominator. Second term, 1/2 times 8 kilometers would be 4 kilometers. Then 2n plus 1 times 8 kilometers. I'm just going to leave that as 2n plus 1 times 8 kilometers. Or actually, we may as well distribute that. We get 16n kilometers plus 8 kilometers. And then what? What would be a good next step? I actually wouldn't plug in I mean, we could certainly plug in n values now, but since n could be any whole number, I wouldn't do that until the very end. I would recommend isolating d first and then start plugging in n values. That way you only need to solve it once rather than having to solve it separately for each n value. Yeah, we could distribute the -2 here. -2 times 8 would be -16. -2 times -2d would be +4d. Also, let's go ahead and get rid of this 4 kilometers. Let's subtract 4 kilometers from both sides. 8 kilometers minus 4 kilometers is just 4 kilometers. Also, I guess this 8 here really should have been kilometers all along, because that's 8 kilometers minus this distance. Let me fill that in so we don't lose track of it later. Don't want to ignore the units. So it looks like we're left with -16 kilometers plus 4 times the unknown distance equals 16 n kilometers, where n can be any whole number, plus 4 kilometers. And then what? What's next? What else could we do to solve for d here? Yeah, add 16. That combines with the 4 kilometers that's already here, so we get 20 kilometers. And then what's our last step to isolate d here? Divide by 4, so 16n becomes 4n, 20 becomes 5. So I think that works for our general solution for d. D can be 4 times any integer kilometers plus 5 kilometers. Or we could even factor out kilometers and just say 4n plus 5 kilometers. And at this point, I would now start plugging in values for n, because we're looking for all possible solutions, all possible locations you could stand. Before we do, though, we don't want to plug in infinitely many values for n. We don't want infinitely many solutions. We just want to be standing somewhere in the desert between these two towers. So what limitations does that put on the values for d? What's the biggest and smallest? Yeah, between 0 and 8. So let's put together a chart. Let's take a look at possible n values and possible d values. For instance, what are some values we could use for n? Let's try 0. Plug in 0 for n. What do you get for d? Yeah, 5 kilometers. And that's certainly allowed. 5 is one of the allowed values. That is between 0 and 8. Let's see if we can get more. What if you plug in 1 for n? Yeah, 9 kilometers. And that's too far. That's outside the range that we're talking about. The whole equation we set up was assuming that we're standing somewhere between A and B. If you leave that range, our equations don't work anymore. You'd have to set up different equations. So we should ignore that value. And of course, if we plug in 2 or 3 or 4, we're just going to get larger distances. So we can stop there in that direction. But we could also go in the other direction. What other n value before that could we have? Yeah, we should try negatives here as well, because n can be any integer, positive, negative, or 0. Plug in -1 for n, what do you get? Yeah, 1 kilometer. And 1 kilometer is in the range we're talking about, between 0 and 8. And let's go further and see what we get. Plug in -2, and what do you get here? Yeah, -3 kilometers. And that is also outside the range we're talking about. And of course, if you go further to -3, you're going to get -7 kilometers. Note that this repeats every 4 kilometers. From -3 to 1 is +4 kilometers. From 1 to 5, +4 kilometers. 5 to 9, +4 kilometers. So every 4 kilometers, we get another point of destructive interference. But there's only 2 such points in the range we care about. So 1 kilometer and 5 kilometers are the only locations that will work in this region. And that's specifically 1 kilometer from antenna A and 5 kilometers from antenna A. Any questions on that so far? One other interesting thing to consider that I think might help you develop a better intuition for interference in general. How far apart are those locations of destructive interference? Yeah, that is exactly half a wavelength. That's a good thing to watch for. 4 kilometers is exactly half of the 8 kilometer wavelength. Usually you would expect repetition every full cycle, every 1 wavelength. But the fact that this is only half of a wavelength, let's take a look at that and investigate that in a little more detail. Let's say you're standing at some location, in this case, the 1 meter mark. So wave A is traveling this distance, wave B is traveling this distance. That leads to destructive interference. To get to the next location of destructive interference, you move 4 kilometers. That means A has, or XA, the path traveled by A, has increased by 4 kilometers. And what has happened to B? Yeah, A has increased by 4 kilometers and B has decreased by 4 kilometers. So we've actually got 8 kilometers worth of change here. A is increasing by 4 kilometers and B is decreasing by 4 kilometers. So the difference is increasing by 8 kilometers or changing by 8 kilometers. And mathematically, this goes back to the 2D in the delta X formula here. Whatever change you make to your position, you get twice that much change to the actual difference in path length because you're changing both of the path lengths by that much. So in order to get 1 wavelength worth of difference or one wavelength worth of change to delta X, and therefore 1 full cycle of change, you only need to move half a wavelength of distance because you're changing both of those path lengths. So the effect is doubled. Any questions on that? One other interesting thing to watch for in cases like this, especially if you're talking about a location somewhere between 2 sources, is what happens if you're standing exactly in the center. If you're exactly in the center, in this case at 4 kilometers, what do you notice about the path lengths? Yeah, they're equal. In the exact center, XA is the same as XB, so delta X equals 0, which means that the entire position term drops out of the equation. And if that's 0, if that whole thing is 0, what would you usually expect the interference to be if this is 0? In this case, we do get partial interference. Why is that? Why doesn't 0 lead to constructive interference as it usually does? What else? Yeah, there's this difference in phase shift. So the location alone, if we're just in the center between 2 sources, I would usually expect that to be constructive interference because there's no difference between the 2 waves, except in this case, there is the difference in phase shift also. So the distance alone would suggest that this would be constructive interference. But the fact that there's also the plus pi over 2 from the phase shift difference makes it partial interference instead. So that's also something to look for. If there's no phase difference, If everything about the sources is identical, if they're same frequency, same wavelength, oscillating in sync with each other, then I would expect the exact center to always be constructive interference. If the exact center is not constructive interference, that means there must be a phase difference that's causing it to be different. And usually the most common phase difference you see is exactly pi. It doesn't have to be. Like in this case, the difference is pi over 2, a fourth of a cycle. But one thing to watch for is if the exact center is exactly destructive interference. Destructive is how much of a cycle away from constructive interference. How much of a cycle is it from constructive to destructive? Yeah, that's half a cycle. And half a cycle is how many radians? Pi. So yeah, the exact center, if there's no phase difference, the exact center is automatically going to be constructive. If it's destructive instead, then you know there's a phase difference of exactly pi, half a cycle. So that's something to watch for. If the point in the exact center is destructive, you know there's a phase difference of pi, and vice versa. If you know there's a phase difference of pi, then the exact center will be destructive. In fact, a phase difference of pi, since that's exactly half a cycle, that basically takes everywhere you would expect to be constructive and makes it destructive instead, and takes everywhere you'd expect to be destructive and makes it constructive instead. So a phase difference of exactly pi, half a cycle, just flips everything exact opposite of what you'd expect. Any other questions on that? If the total phase difference is 0, yeah, if the total phase difference, the whole thing is 0, that's going to be constructive. Because total phase difference tells you how much offset the waves are at the observer's location. If there's no difference between the waves, then that means that they're constructive. There's no offset. And that might be because there's genuinely no difference, or maybe there are several differences, but they cancel out. Like maybe there's a difference in path length and a difference in phase shift that cancel each other out to get 0. That would mean constructive interference. Or if these values all add up to a total difference of, let's say, 2 pi, that's exactly one full cycle offset. So this crest lines up with the next crest on the other wave, and you still get constructive interference. As long as the total difference in phase, delta total phase, is a whole number of cycles, that is 2n pi, then that's constructive. Any other questions on that one?
Yeah, can you go over how we got, or what -2d means again?
Yeah, -2d over here. That was ultimately from subtracting xb minus xa. And we were saying xa is just defined as this new variable d, where d is the unknown distance from antenna A. And then xb has to be 8 minus that, because it's whatever left over. We've got 8 kilometers to work with. We're calling the first some number of them d, and the rest of it is 8 minus d. And then to find delta x, the difference in path length, we're subtracting distance b minus distance a. So algebraically, that's 8 minus d minus another d for the distance traveled by a. When you subtract those, the minus d and minus d combine to get 8 minus 2d. And more conceptually, you could think of that as the difference between them is, like, let's say you've traveled some distance from D, or some distance from the first antenna. You've gone that far from the first antenna, but also that much closer to the second antenna. So the effect of your walking is doubled, because you're walking away from antenna A and towards antenna B at the same time.
Okay, that makes sense. Thank you.
Mm-hmm. Any other questions on that so far? And one other scenario that often shows up, in some cases, maybe instead of standing between these antennas like it's describing in this problem, suppose you're standing somewhere outside the antennas. Let's say you were standing over here. In that case, we're going to have to manage the distances much more differently, because you have some distance from B and also some distance from A. And in this case, let's call those, in this case, let's say the distance from let's say the distance from B is L, some length. XB is some length L. And then how would the distance from A be related to that? Yeah, that'll be, well, not X plus L, but what is this extra distance? Yeah, it's specifically 8. So if antenna B's wave is traveling from here, some distance L to your receiver location, antenna A is traveling 8 kilometers in advance and then an extra L beyond that. So XA is going to be 8 plus L. And when we subtract those, again, B minus A, we've got XA is 8 plus, or XB is L. Then we subtract 8 plus L. And what do we get when we subtract those? -8. What would happen if you moved a little bit? Let's say from here, we move another kilometer, increasing the distance wave B has to travel and increasing the distance wave A has to travel. Now what happens to delta X? We're adding 1 kilometer to B and we're adding 1 kilometer to A. So what happens when we subtract? If you got 8 plus L plus 1 and then L plus 1 and you subtract, what's going to happen? Yeah, it's still -8. The extra distance cancels out. Because if you're outside this range, you move a little bit further, you're increasing both distances. So when you subtract, that extra distance cancels out. The difference between these is still 8 kilometers. Because no matter how far away you are, the difference between these is 8 kilometers. If you move a very long distance away, the difference between these two paths is still the extra 8 kilometers. Or if you move really close, then the difference between these two paths is still the extra 8 kilometers. So if you're standing inside this range and moving around, you're changing delta X. So you get a variety of different interferences depending on where you stand. But if you're outside that range, you move around and the delta X does not change. Delta X is a constant. So as long as you're moving along this straight line, delta X doesn't change when you're outside this region. And so that means all these locations on the outside are just going to have one type of interference. We could plug in -8 for delta X. In fact, let's go ahead and do that. If we just write out our total phase equation, removing the time term because that doesn't matter anyway. We know delta X is -8 kilometers. We know wavelength is also 8 kilometers. We know phase shift is pi/2. So we can say delta total phase is, there's no delta there anymore. We plug that in. Simplifying this, the negatives cancel out, the 8 and 8 cancel out. So we just get 2 pi plus pi/2, which equals 5 pi/2. So what type of interference is that? Yeah, over here you get partial interference. And as you move, that doesn't change. If you're moving in between them, you go from destructive to constructive to destructive to constructive. But once you get outside this range, you've got partial interference and it just stays the same partial interference no matter how far you travel. The signal is ultimately going to get weaker just because you're further out, so it dissipates more due to the inverse square proportionality, the intensity idea. But the interference type doesn't change because you're not changing even though you're changing the distances from both antennas, you're not changing the difference between them. And the difference is what matters here. Any other questions on that so far? All right. Let's take a look at the double slit experiment as well, because there have been some questions about that elsewhere that I wanted to address. So going back to the double slit experiment, let's say we have our wall with a couple of holes in it and some light shining on that. And then somewhere else we've got a screen or a wall that the light is hitting. And let's assume there's no sneaky modifications. We just have an ordinary double slit experiment. In the exact center, what would we expect to see? Yeah, that's going to be a bright spot because both of the rays of light are traveling the same distance. We've got complete symmetry here. The rays of light are traveling exactly the same distance. So we're going to get a bright spot, constructive interference. So I'm just going to draw that as a bright highlight. And so that's going to be, we could call that n equals 0. N being basically a count of which bright spot we're talking about. And we had an equation last time to describe that. What was our usual equation for where to find bright spots? Using the wavelength and the theta and all that. Like if we have some angle of elevation here, what equation could you use to figure out if that location is a bright spot or a dark spot? If we do want a bright spot, if we want constructive interference, what has to be true about this angle? Did we get an equation for that last time? Based on the sine of the angle? I think what we ended up with was d, the distance between slits. Yeah, the path length difference is d sine theta. So d sine theta represents the difference between path lengths. So you've got this path and you've got this path. And one of those paths is a little bit longer. We ran the geometry last time and found that that difference in path length is d sine theta. So d sine theta is the little bit of extra distance traveled by the longer path. And if we want constructive interference, that has to equal a whole number of wavelengths. And this goes back to the idea of like if you're standing in the exact center, they're traveling, the two paths are the same distance. But you don't have to have the same distance to get constructive interference. You just have to have a whole number of cycles. So this equation is basically saying the extra distance traveled by one of the waves is a whole number of cycles, a whole number of wavelengths. So this guarantees constructive interference, assuming there's nothing else different going on, if the only difference is path length. And the n here basically just represents which bright spot you're talking about. So the center is n equals 0, the central maximum. The first bright spot beyond that is n equals 1. The next bright spot would be n equals 2, and so on. And a useful substitution we can use here, the theta here is the angle of elevation. That is this angle here. That's the theta we're talking about. But it's often useful to label this not in terms of the angle, but in terms of the height. We want to know how high is that on the wall. So if we call this distance, and let's say we just call that distance y. And then The distance from wall to wall, let's say we call that distance capital D, I think is usually what it's called. Sometimes capital L, depending on the textbook. Does sine theta incorporate these distances? You mentioned y over d. What would y over d be in terms of this angle? Is that sine theta? Right, that's tangent of theta, because that's the opposite over the hypotenuse. But if this is a very small angle, let's make this much smaller, because we're usually just talking about values near the center anyway. If theta is very small, then this diagonal distance is pretty close to d anyway. So that means y over the hypotenuse, which is sine theta, is almost the same as sine theta. So it's at very small angles, tangent theta and sine theta are almost the same anyway. So if we replace sine theta with approximately tan theta, which is y over d, we get little d, the distance between slits, times y over big D, the height over the distance between walls, equals a whole number of wavelengths. And if you solve that for y, you can take the n times lambda, multiply by big D, and divide by little d. So this actually gives us a formula for y in terms of n and all these constants, because lambda, big distance, and little distance, those don't change. So we get y equals n times a constant. So if you calculate lambda times big D divided by little d, that's the distance to the first bright spot. So the first bright spot is going to be at a distance of lambda times big D times lambda times big D divided by little d. The next one is going to be that distance times 2. So the same separation. And then that distance times 3, that distance times 4, and so on. So assuming the angle is small enough that we can use this approximation, the bright spots should be evenly spaced. 0, 1 lambda d over d, 2 lambda d over d, 3 lambda d over d, 4 lambda d over d, and so on. Bright spot and constructive interference. The thing is, no matter where you're talking about the rays, we're talking about rays hitting the same spot on the screen. Even if it's a dark spot, we're talking about rays hitting the same spot on the screen. But a dark spot occurs when you have what sort of interference? Yeah, destructive. So destructive interference, that doesn't mean the rays aren't hitting that spot. It means they both are hitting that spot, but they're doing so in a way that cancel each other out, because the extra distance traveled by one of the waves is exactly half of an extra wavelength, or something and a half wavelengths. So it's the difference of something and a half extra wavelengths and both of them hitting the same spot that causes them to cancel out, so we get a dark spot. So we should expect those bright spots to be evenly spaced with a spacing of lambda d over d. But note that that depends on wavelength. If you change the wavelength using a different color of light, you're going to get the same pattern but spread out a different amount. So if you shine red light on these slits, you get this sort of pattern. If you shine blue light has a shorter wavelength, so you're going to have closer together bright spots. So the blue light might look something like still a bright spot in the center, but then the other bright spots will be spaced closer together. And so if you're shining red and blue light, you're going to get these two overlapping patterns, including some purple spots where the red and blue light overlap. In fact, if you shine white light on this, white light is all colors at once, they're all going to split up differently, and you're going to end up with these sort of rainbow spectrum patches on the wall as the light splits up, and red is spaced out some amount, orange is spaced out a different amount, yellow is spaced out a different amount, and you end up getting these rainbow patches from these individual spectra. Any other questions on that? All right, and that is it for today. I will see you next time.